So for the digital to analog converter, the DAC 8574, the only thing I've actually been able to find online for this is a app note for using it with an MSP430 F-Series microcontroller from Texas Instruments. And of course, they're both from Texas Instruments. Everything else I've been able to find on my looking have all been about PCF 8574s, which of course are not digital to analog converters. They're a I2C serial to 8-port port expander, which of course is not what we have. So anyway, looking at this app note, what I find here is it basically gives a few examples of hooking it up. And so there's an interface diagram using the MSP430, I2C lines, just basically decoupling caps, all the outputs, 0 to 5 volt analog output, all the address lines are hooked to 0, which is what I have, so theoretically this will is pretty much as close as I can find to what I have. Instead of the MSP430, of course, I have an ATmega 328. Basic principles of operation, I2C bus timing, LDAC functionality, multi-channel. That's talking about having loads and loads of the generating a sine wave. Oh, that's something we should give it a go. Give it once we get the basics working anyway. And there should be something in here about how to drive this thing. Here we go. Software code. So it looks like this thing is an example of using the chip to generate, by the looks of it, a sine wave. Now of course we want to just get the thing working for the moment, but you know, maybe we'll see what we can glean out of this and get to grips with the basics first and then try and make a sine wave out of it. So important things that we can get out of here is that the DAC address for the I2C bus is 98. Data control, this is saying 34, which is a broadcast to all DAC channels. I'll have to look at what that means. Standard pin, SCL, these are I think register lines for pull-ups and things, and the trigger point. Looks like a table, 16-bit values for generating a sine wave, so we'll maybe poach that when we give that a go. And here's the main code, so let's have a look what we've got here. DAC address, sending a start command, stop command, loading the DAC control byte. That was the 34 before. The DAC address is here. So we're sending out a control byte to the address, and then it looks like reference setting up FF, because there's 256 values in that table above. So it looks like we're loading a register with the 255, getting the value 0 into the other. It's probably a 16-bit register and you're loading it 2 bytes at a time. Loading up the data from the sine table, bringing bytes into the I2C registers, sending the data out, and basically looks like looping with an increment in here as well. Down here, so we're incrementing the value, doing a couple of checks for rolling over and going back and starting all over again. So this looks like the main loop. So it looks like you go set the address and then you start just piling data out. So we'll have to look at how easy that is to do that. But it looks like the main thing is you set the initialization byte, control byte, and then you send your data out. So we'll look at what the control byte means. We'll have to go back to the datasheet for that. The rest of this looks like initialization routines and things for the basic microcontroller. So I don't think there's anything particularly nasty there. So let's see how we can convert this into an Arduino sketch from the assembly language SPI code. Alright, back to the datasheet for the DAC, and what we got here is the control byte is got, looks like 2 address lines, load mode bits, where 00 is store I2C data, most significant byte, least significant byte, potentially power down information. 01 is updating the DAC with I2C data, most commonly utilized mode, this contents of MS byte and stored in temporary register and the DAC register of the selected channel. The mode changes the DAC output of the selected channel with the new data. So we want to be, when we write the data, we want it just to get reflected right out. So that looks like the one we want for these 2 bits, the 01. So we'd have 00 for the 2 address lines because we've got everything tied low. Looks like we want 01. So the first high order of the control byte wants to be 1, not 3. The 3, which is this bottom one, is broadcast mode. And I'm not sure why they're using that in the launchpad of the MSP 430 version, but we've only got 1 chip on here and we want to talk specifically to 1 register to set the value, so we'll leave that at the 01 setting. Second half of this is the 2 bits are what channel you're writing to, so 0, 1, 2 and 3. Well, actually bit 0 is PDO, so it basically looks like you would have to output 2, 4 or 6, not 2, 4 or 6 to address channel A, B, C and D. We're not going to power down the thing, so we'll just have that least significant bit set to 0 as well. Yeah, so the load, we're going to use this one, 01, right to the data. So you write the control byte, and you write your 2 data bytes. I didn't find anything else for this. Yeah, there we go. Standard slave receiver. You output the slave address, which was indicated above as 98. Then you send your control byte, then you send your most significant byte, then your least significant byte. And then I'll assume you rinse and repeat for any other registers and things. So that's pretty straightforward. Yeah, I think we have enough information there now. So I'm going to go away and see if I can put together the beginnings of a sketch to talk to this thing, and I'll just add it to the existing one we were using for the A to D converter. I'll just comment out the code for the A to D for now, and we'll just focus on the D to A. Okay, I've been busy writing a bit of code. I've pulled in as much as I can, and while I was at it, I created a table with the sign values that were included in the TI MSP 430 example. So we see if we can make a sine wave out of it. That would be kind of interesting. Anyway, what I've done is I've included the wire interface, of course, for the I2C. So in the code, we saw that this was using address 98. Control code is set to 34, which was used in the example, and as we've already looked at going through that code and also the datasheet, we're going to probably change this because this is doing a broadcast. This is the sign table, so that's what we'll look at in a moment. In the setup, we've added the wire begin with the DAC address in it so that it sets up the initial address. That's the only thing we've added in there that's new. In the main loop, I've commented out for the moment all the other things. I've created a subroutine rather than have a massive big thing duplicating the same code. I created a subroutine that basically allows me to pick the channel I write to and send a value in. So what we've got here is a temporary holder for the DAC command, which is effectively going to be that 34 equivalent that was up at the top. And I'm going to give it a channel number, 0, 1, 2, or 3. Based on the channel number, I'm adjusting the command. So we've got the 1 bit set the value you send automatically effective on the output. And then you've got the address 0, 2, 4, and 6, which we were saying is the ones that let you select channel A, B, C, and D. If I give it any other than 0, 1, 2, or 3, we'll just hit the break in the switch clause and it will be ignored. We'll then start the standard wire begin transmission with the address of the DAC. We send a wire.write command to it with the command, so it's automatically going to prepend the address when it sends this. So it will do the address, which is 98, the command, which is going to be, say we pick channel 0, which would be 10, and then the value shifted right 8 bits, because remember we're sending a 16-bit value and we're sending it a byte at a time. When you used it wire.write, it actually only sends a byte. It won't send a 16-bit value. We want the most significant byte to go first. So we do the wire.write value right shift 8. That's rather than divide by 256, which is going to be really slow when you start bringing math in. If you just use a logical shift right by 8 bits, it'll actually be much quicker to do that function and give you the byte in the right place. And then we just do another wire.write with the value. In this case, it automatically ignores the upper half of it, which we just shifted out in the previous statement. And that basically is the code. And then we got end transmission, which would send the stop bit. And all we're going to do is basically set DAC 0 for about quarter of its value. So it should be 1.25, 2.5, 3.75, and effectively 5 volts is what we should see, or within the accuracy of the D to A converter anyway. So let me just upload that, and it's going to sit there and do that in a loop as well. So it's going to keep outputting it so that if we do have any issues, we can investigate. So let me just upload that code. All right, that's done uploading. Okay, program's now running. Everything's uploaded. So we're going to just probe the output 0. Oh, that's not 1.25. Output 1, nothing. Output 2, nothing. Well, millivolts anyway. So there's nothing on there, so we need to have a look at what's going on. We're outputting to address 98. Now, I suspect that the address might not be right, because the I2C bus doesn't go above 127 normally. So 98 did seem a bit suspicious, but it's right in the code there. So I think I'll just have a quick look at what's happening, and we'll get back to it. Just one sec. Just set up my Tektronix MDO 3054 to capture the I2C bus, and we'll see what we can find out as far as what's going on here. So I've just reset the Arduino Uno. It's just going to let go of the reset button now so we can capture a waveform and have a look what's going on. Do this. Just need to capture a bit more data, so let's just run that again. Oh, I guess we got plenty that time. So let's just zoom in on here. So it looks like it's writing 18s everywhere, nothing else. That suspiciously looks close to 98 with 1 bit missing. If I look at the event table this time, yeah, that confirms it, and it looks like there's missing acknowledgements for all of these, which means that there's no device listening. So let me just do a quick bit of Googling, and I'll get back to you. Okay, just checked on the Arduino website and just had a look at some of the code, and yes, true to form, the address is actually 98 when you look at it on a pure binary aspect, but the libraries take whatever address you give it and they shift the value left 1 bit so that it makes room for the read-write bit, which is normally just toggled on the least significant bit of the address, so that the chip knows whether it's being told to read or write. So what that means is we need to change our address from 98, which of course it's dropping that most significant bit off. We need to change it to it would be 4C. So if I just change this in my code now, all right, 4C, when it shifts left 1 bit, gives you 98. If you don't believe me, bring up a hex calculator or write it down and you will see. Anyway, I'm just going to enable this in the code. So you can see how useful it is to have something that can actually do protocol decoding. That very quickly showed us that even though the Texas Instruments code was using address 98, with the Arduino libraries, the way that they're coded, they're actually only allowing the addresses to be the lower 7 bits of the address, and they're actually shifting them when they're putting them out on the bus, which means you're losing the most significant bit. Alright, I've just changed that code now. I'm going to hit the reset on the Arduino and resample on Tektronix oscilloscope, and we'll see what we get this time. So I'll let that go. Okay, well, I need to zoom in there, but that certainly looks a lot healthier. And oh, okay, there you go. So it's showing me 4 C's now as far as, let me just widen that out a little bit, bring it into view. So now we've got 4C, which is the 98 less a bit. So the oscilloscope is actually taking the address bit off as well for its display. So obviously that aligns with that. And we are sending out, if I read off the code there a second, the first thing we send out to the controller is 10, then a 12, then a 14, then a 16. But in between that, we're also sending out the different values. So 4,000, 8,000, C1000, and FFFF. So if we look at this on the oscilloscope now, it's showing us that, let's just take it as being address 4C. We're sending out the 10, 40, and then we're sending out 4C again, which is the address again, and we're sending out a 12, and which is addressing channel B. So the 10 was addressing channel A. This is addressing channel B with data 8, which is the halfway point. And if I just scroll across a little bit, you'll see that it's 80. And we got 4C again, and the next one, which is channel C, we got C000, and then we should have, if we're lucky, we've got 4C again with channel D, and it's FFFF. So it looks like now that's working. Very minor bug, but of course, being able to throw it on a protocol decoder just using 2 wires speeded up the diagnosis really. So let's get this back on meter and see what we're reading now. So I've just put it down there. I haven't got the probes connected yet. I'm just going to. So we should have 1.25 on channel 0, i.e. channel A, sorry. So that's channel A. So it's 1.258. So a little bit high, but we can use software. You can calibrate these things. That should be 2.5 volts, so 2.509. And channel 3 should be 3.75, 3.758. So certainly within, fractions of a percent. And the last one should be 5, and it's at 4.991, so a little bit low. So there is, room for improvement, and as I say, you can do this in software. The 16-bit DAC certainly seems to be working there now that we've got the address correct. So now we've got a analog to digital converter running on the SPI bus, and we've got a digital to analog converter running on the I2C bus. So you know what? I fancy trying to see if I can make that sine wave output. So technically I should be able to just loop it and just run it in a loop going through that array, like a for x equals 0 to 255, grab the byte and just send it out, because this little function I've got, set DAC, if I just send it to one channel with the value, everything else is happening in here. So let's just see what I have to do to make that work, and see what kind of output we can get, see how good it is. Alright, so I've just commented out the output to DAC 0, so when this goes through, it'll set DAC 1, 2, and 3 to their respective values, and then at the end of it, as part of the loop, I've just put a for x equals 0 to 256, x++, set the DAC output value equal to the position within the sine table that we had above there, that I ripped off from the TI application note. So I think that's actually going to do once, and then it's going to go through, so it's going to be a bit of an ugly sine wave. So you know what, I'm going to set this so that it'll stay there forever. So while 1, and we'll start that forever, just for the sake of seeing what happens here. I think that should be good enough. So that will stay in here, running through the sine wave again and again and again and again. So let's see if that compiles. Yep, so it's done compiling. Let's upload that, and while that's uploading, I'm just going to hook up the oscilloscope to the output of the first DAC, and we'll see if that works. It should be nice. Alright, for the sake of the display, I've basically turned off some of it, so I've still got the I2C sitting on the top. In here, if I can just figure out how to move that, I don't know if I can, but here's channel 3. I've just set it on the bottom so that I've got 2, 4, 5 volts, so it should stay just below the I2C. You know what, I'm going to just turn off the I2C. We know that's working, so let's just turn it off, and we'll set that to the middle. Get rid of that, and we'll say go, and that should have captured something. It looks a little flat. Maybe we're just going a bit too fast for this thing. Oh, there we go. Well, that's not too bad. It's sitting on, of course it's not centered around 0, so if I just set it up to 2.5 volts for its offset, roughly, and we'll just capture that again. And that's actually not too bad a sine wave, so that's what it's doing there. Its frequency, I've actually got this measuring the frequency of channel 3 and 2. Its frequency is only 9 Hertz, so that's a fairly tight loop using wiring, reading the 16-bit values. So whilst it is producing a nice sine wave from that table, looping it through 255 times and only doing, the 16-bit values as flat out as it can, it's only managing the 9 Hertz. I think if you wanted to have a higher frequency, you probably would want to reduce the number of bits. If you simplified the table to just 8-bit values, or significantly reduce the number of samples, because we've got 256 samples, so we're outputting a huge amount of data. Now we probably could increase maybe the I2C bus clock speed, because the chip will handle up to 3.4 meg. I haven't tried changing that frequency to see how well it will do, but that's an option. But anyway, that's not the purpose of this little video. What I wanted to show is the fact that we can quite easily now set up an analog to digital converter, a digital to analog converter, to significantly increase the resolution of the Arduino Uno. Because if you remember the previous video we did, it was only using 10 bits, and if you consider how accurate this is with the external A to D converter and the D to A converter, and how stable those are, it was keeping the readings to well below a millivolt as far as stability is concerned. So let's just go back to that and have a quick look and see how accurate it really is, at least at the low end, and just have another look at the fluctuations on that. Just going back to the original program that was the sample. I know it's pretty basic, but I'm pretty sure we can actually make it look at more resolution. See, on the V out here, it's just printing V out, and the default for printing decimals or longs is to only print 2 digits. So I'm going to do a (4) and allow it to actually go down into the nanovolts to the display, and I'm going to bring up the meter here as well. So I'm going to hook up this to the A to D converter input, sitting where we left it before. Start the monitor on Arduino. As you can see here, it is much more accurate as far as the number of digits are concerned. So that's 1, 2, 3, 4, 5, 6, 7 digits that we're reading on here. Well, 8 if you include the first one. So that's way more than we would normally use, and you can see that it's actually only really fluctuating on the last couple of digits. Let me just adjust the voltage a little bit to get it away from the turning point. So it's sitting at 1.14. The DMM is reading 14677. I'm reading 14687. So it's still a little bit higher on the A to D converter, but what I want to show you here is the fact that this is the millivolts, this is the microvolts here, and this very last one is down into the nanovolts. It's really still only fluctuating on that first one, maybe 100, not even 100 microvolts, because that's 69, 68, 68. I'm not seeing anything less than about 68 there, and it's going up to 70. So it's probably fluctuating maybe 30 microvolts on that. I am using a proper voltage reference to feed the 10-turn pot, so that's a lot more stable for the sake, because if I just hook it up to the power supply, which I'd done earlier for earlier tests, it would be jumping around a lot more because of the noise on the supply. So in this case, if we're wanting to set a power supply up and control it, you're talking 1.1%, 0.1, 0.01. You probably being able to get 0.01% accuracy, but definitely, that's without any calibration and software compensation for the readings. With a bit of software compensation and things like that, and allowing for the fact that once it's in a power supply and not on a breadboard, it should be even more stable. You're probably easily going to be able to maintain certainly much better than 0.1% resolution. That's nowhere near what 24-bit is capable of, but it's going to be more than enough for the power supply. And I think that I happen to have these 24-bit ADC. What I will do in another video is maybe try some other ones. I do have some 16-bit ones, and we'll see if they are as stable as this. So one of the reasons I'm suggesting that is because even though you go to 16-bit, there is still issues with effective bits versus actual bits. So like a 24-bit ADC, you can see here that even though I have the resolution to go down to sort of nanovolts, it's not really very effective. It's jumping around quite a bit, and really only having down to 10 microvolts would probably be more than enough, or even just millivolts and maybe 0.1, 100 microvolts would be enough to control a power supply. The rest is there if you ever wanted it, but what I would say is that if you were going down to that level, then you would start leveraging that low end. You would start leveraging the programmable gain amplifier and automatically adjust it so that you're amplifying the signal up rather than trying to work in the low end of the A to D converter. So I've just cranked that back down to 8 millivolts. If I increase the gain, then I would have less analog to digital conversion noise from the sampling and everything else, and potentially would have a much better resolution. Once we start getting into writing some full-blown software to control the power supply, then we'll look at things like that as an option. But for now, I think that pretty much completes it, except for looking at flipping the ADC to use 5 volts instead of 2.048 volts. So let's just do a couple of reconnects, and we'll see what software has to be changed to make that happen. So this is the data sheet for the analog to digital converter, and I'm on page 36 of it, looking at the configuration register map. So there's only 4 registers for this, and register 0 has the multiplexer, the gain control, and the programmable gain amplifier bypass. So we're not using any gain control right now. So with register 0, this is the table right here. This is where you can actually select which analog input you're reading from. So right now we were outputting, if I go back to the code here a second, this is the initialization in the ADS1220 C++ file. So we're sending out a 01 to register 0 and an 04 to register 1. And what that means is we're sending out an 01 to here, so the mux is 0000, which means that's the default behavior. So the analog input positive is analog input 0, analog input negative is analog 1. The gain is set to 0, which is fine, and our PGA programmable gain amplifier is also bypassed. Now, what we probably want is the voltage reference settings, which means it looks like it's control register 2. that allows us to change the voltage reference by the look of this. Yeah, so let's just scroll down, see what that is. That's that one. Control register 1 is sampling rates, operating mode, conversion mode, temperature sensing, burnout detection. So register 2 is, yeah, here we go. So what we set for register 2 in here is 10, so that's 10 hex. So if we go back to the code, we've got 000, which is off for the current settings for the outputs. Sorry, that's the allowing you to have excitation current going out of the analog inputs. Low side power switch is also 0. So we have a 01 in here for the filter FIR filter configuration, which is simultaneous 50 and 60 hertz rejection, which is excellent. We want that, and we want to keep that. And what we have on bits 7 and 6 though is the voltage reference selection. So right now it's set to 00, which is the internal 2.048 volt reference. So we want to change this to use the ref P0 and ref N0. I've connected N0 to ground, and I've connected the P0 to the plus 5 volt output of our ref02 precision voltage reference. So it looks like we want to have 40 hex added to whatever value we're currently putting out. So we would probably want to put out 41 hex on that byte there. Sorry, not 41, that's 1, 2, 4. Yeah, sorry, 50. So we're adding 40 to it, and we've already got a 10 there. So we want to change this here, which is what 10. We want to add a 40 to that, so we'll make that a 50 hex, which is the 40 hex and the 10 hex, and save that. And if I recompile an output, theoretically it should now read from the or use the analog external analog reference inputs. So I'm just going to set my meter here so that I can just check a couple of things. So I want to set this to a value that I know would normally read, so because I'm doubling, more than doubling. So if I set 1 volt on here, or 2 volts on the input, which I'm just setting up on my DMM right now, just approximately, then normally it would show me roughly 200 millivolts from the 2048. So because I'm going to 5, I expect that it's going to show me a little bit less than 1 volt because I haven't changed the math yet on the code. So if I save that, go back to the Arduino code, and just recompile that, because it will automatically pick up on the changes that I set, and have a look now. And we'll see, yeah, it's now reading 821 millivolts, which of course is completely wrong based on the fact that I've got 2 volts going in, but it's what we expect because the voltage reference is now different. So that shows me that it's picked up in the voltage reference. Now what do we have to do to make it work with 5 volt reference instead of the 2 volt reference? So here we have a define for vref, and you can see everything else is being calculated. So that's a really nice piece of code where all I have to do is basically copy that, and I'll comment out the original one just so I have it there, and I'll change this one to 5.000 for our new voltage reference, and I'll output that instead. So that's now going to recompile and output to the Arduino Uno, and with luck that's all we have to do to now get the new range out of this thing. So let me just have a look at that. So now it's showing me yep, that's good. So I have 2.0037 on my DMM. If I just put this next to it, hopefully it will stay focused on both of them. and I've got 2.004, so that's pretty close to each other. Now theoretically now I can go all the way up on my 10-turn pot to 5 volts without this thing messing up on me, which would be nice. So that's up to 4 volts, and it's tracking nicely, which is really good. So let's see if I can get this exactly to 4 volts. 3.999. Even a 10-turn pot when you're dealing with fractions of a percent is still quite hairy. So I got 4.002 on the DMM, and I got 4.004 on the ADD converter. So that's yeah, within 0.1, well, way within 0.025% of each other, and definitely within the resolution of my Agilent, and so that's showing us a really nice accurate reading. So let's crank this all the way up. That's as high as I can go. So because it's on the pot on the end of a piece of wire and everything, I can't quite get 5 volts out, but 49.5, and I'm reading 49.53 on the ADD converter. So there you go. Very minor bit of code change. One extra couple of pieces, well, 2 pieces of wire added to my circuit, and now we have a 0 to 5 volt output. Very stable for readings, down to microvolts quite happily, and so with coupled between the digital to analog converters that are able to go from 0 to 5 volts and the analog to digital converter now that can read 0 to 5 volts, the next step would be to add the power stage to this that we were looking at in the previous video, and make it a complete computer controlled system. So I think that pretty much covers everything that I wanted to show in this video. Just trying to think if there's anything else. I don't think there is. I'll post all of the code and things like that, and links to the data sheets when I put up the video, so that you can go look at them yourself. As usual, if you like what you see, give me a thumbs up or a like, depending on where you're watching this, and I'll bring up the next video soon. So it probably won't be on the actual fully integrated system yet, because I'm still waiting on a couple of minor parts to come in, and like I say, I want to use the 16-bit adapters and a prescaler that I have as well on my final, like my more advanced design. So they may take a few weeks for those to come in. We have plenty of other areas that we want to look at, one of which being one of the viewers suggested for the high voltage, for the high side FET, to get the extra volts above the standard supply rail would be to wind a few turns of transformer wire onto the toroid in addition to what's already there. So I've done that before, or similar to that, a long time ago, but what I will do is I'll take the toroid off, unscrew it off the board, and I'll put together a little video showing how you can do that, and we'll see how effective it is. We don't need very much current at all, because as we've already seen, the input to the MOSFETs is 0 current. It's only the ancillary circuitry that's going to be drawing anything from it. So I think that might be a very viable thing to do. So anyway, that's probably going to be the next video for the power supply project. This completes the video for now as far as analog to digital conversion, digital to analog conversion. Of course, within your own designs, you can choose to use whatever resolution A to D and D to A converters that you have available or want to buy. And if you don't want to use computer automation for your power supply, that's fine too. Everything we're doing outside of that is perfectly valid, and you can just build it to the way you want. Anyway, that's it for now. So I'm going to sign off in this one, and I'll see you again soon. Thanks.